Hi, so I think last time I said I'm going to look more at conservative vector fields, but it's actually 16.3, not 16.2. So we're going to actually look at line integrals first, then we're going to look at conservative vector fields. So what is it that that we want to do? We want to basically integrate not over just a piece of the real line, or actually we don't want to integrate in several variables. We want to do a one variable integration, so just a single integral. But we don't want to do it just over an interval over a real line. We want to do it over a curve, right? So we maybe have a curve, let's call it C, in the plane. Let's say that could be in three space or however many variables you have. But let's just start with a plane, and we have some function f of x, y, z. This is defined on C, and what we want to do is we want to integrate over C f of x, y, z with respect to the so-called length length measure. We're going to write ds with a little s over here. Now, what this means is that well, if this was in the plane, then I can think of if this is in the xy plane, right? Is this curve C? If I think of the graph of f, oh sorry, I wrote it in a plane, so there shouldn't be a z. There can be a z if we do it in three variables, but let's just do it in two variables over here. So if I think of a graph of C, of f over C, well, it's going to be, at each point in C, f has a certain height, right? And so the graph will be, well, that will actually be some curve in three space, right? But now the point is that we're going to have sort of this fence going along. So think of C as a line on a map, and we're going to put up a fence, and the height of the fence that's the value. That's what f is, right? So at each point of the fence, it might have a different height, and so this is supposed to be, again, area under f, whatever that means. What's the area of this fence, right? So it should be, basically, it should tell us, if we wanted to paint the fence, then it should tell us, the amount of paint that we're supposed to use. All right. Well, how can we set this up? Well, the way that we set this up, let me draw sort of a smaller piece of this curve C, and the way that we set this up, we could cut C into little pieces, right? Each one of those I'm going to call delta sub s, maybe delta sub si, because each one of them is going to have slightly different maybe width, but these are really, really, really tiny pieces of the curve. And then above each, there's this fence goes like this, and I have, if I look at, basically, I would put up wooden planks with height. This is f of xy, right? This is the height of the of the fence, right? So what am I doing? I'm really, this thing is the limit, whatever limit. Let's not worry about how we take the limit, basically as the delta s, I'll write it in quotation marks here, as delta s goes to 0. That's basically the limit that we're taking, and we take a sum of f. Well, at each point, at each little piece here, we pick some point xi, yi, right? And so xi, yi, delta si. It again looks very much like the definition of the integral for in one variable, right? So the point is, if you start modeling some problem and you end up that there's something that looks like this, you can compute it as an integral, right? And well, the thing is that this is the thing that you want to compute, but these things, well, we're going to have lots of calculus that we can use that are going to make this easy, right? That's sort of the point. It was easy to compute with calculus. All right. So how would we compute this with calculus? Well, we have a curve. We could parameterize with some vector valued function. Let me just do it in 2 variables. Write down what it means in 3 variables in a moment. It's basically the same thing. But I have some vector valued function c, where t goes from a to b. That's parameterized as our curve c, right? Those where t is a, and then as we go over here, those where t is b. Okay, so now the thing is how to use this. Well, we want to figure out, write it down. So f x y ds. We want to figure out how to write it in an integral that we can actually compute in a sort of a calculus 1 type of integral. So we're going to go from a to b, all right, and then we're going to plug in f of x of t, right? Because that's we're going over this curve, and so we're plugging in points that are on the curve. Now we want to figure out our ds. Now ds is supposed to be in units of length, right? It's supposed to be area, basically, right? Or at least in one of the applications, it's area. So I want to figure out what this ds is. Now this, if we're parameterizing a curve, it generally is that the t is time. We're moving, and as time goes by, we're at various points of the curve. So the derivative of c is velocity. Now velocity is really in the units of length over time, and this integral is going to be in terms of dt, in terms of units of time. But I want units of length over here, right? So how do we get length? If we have time, well, we multiply by speed, right? How far? What is this small piece, little piece here? Well, it's if I have delta t, how long does it take to traverse this little piece? I just multiply that by the speed, and I get the delta si. So I need to multiply by the speed, right? So c prime t dt. Yeah, that's the formula for how do you compute this thing. Well, let's do some some examples. Maybe actually before I do an example, it's the same thing in 3 variables. Let me do a 3 variable example as well. But we have if it is in 3 variables, so f of x, y, z ds, and we have now c is of t is given by x of t, y of t, z of t, right? And this is the integral from a to b. Again, this is the interval where t lives, just like before. F of x of t, y of t, z of t. It's the same thing. Right? It doesn't matter how many dimensions I'm in. Okay, so let's do an example or two. So if we let's look at let's look at maybe a spiral, right? So let's look at a spiral given by cosine t, sine t, t, right? So this is where x and y are going in a circle of radius 1 around the origin, and z is going from, well, let's see where t. Let's say we go once around the spiral. So let's say 0 to 2 pi, right? So that's once around the spiral. So if I draw what it is, right? That means we start over here at 1, 0, 0, and as we go up, by one revolution, right? We get to this is at 2 pi, right? Those are 1. This would be 1 somewhere over here, right? And so it's this curve over here, right? And let's integrate something. Let's do. So let's suppose this is this is my C, right? So C is giving this is the parametrization, right, of this curve. And let's integrate. And sometimes if we don't give another name to the curve, you can just write C over here. And let's integrate. I don't know. What should we integrate? I don't know. X, Y, Z. Yeah. Why not? ds. Right. Okay. So what is this? Well, this is the integral from 0 to 2 pi. We're just basically plugging into the definition, right? So x is cosine, y is sine, z is t, and then there's this. Well, we need to compute what the speed is. Well, the velocity is minus sine cosine 1, right? So that means running out of room over here, so maybe we do it here. So the speed square root minus sine of t squared plus cosine of t squared plus 1 squared. Okay, this is sine squared plus cosine squared. There's just 1. 1 squared is 1. So this is just square root of 2. Hey, this is actually constant speed. So that goes here, dt. So now you just have to compute this. Maybe I picked a slightly wrong example because now I don't want to do it because I'll have to do one integration by parts. So let's not do this. Take up too much time. But it's basically that's just a one variable integral, right? Let me do another one, and you can do this in let's do a simpler one. You can do this in two variables again as well, right? So suppose that my c of t. Let's suppose that this is t squared. Let's suppose t goes from 0 to 1. Now, what is this? This is when x is t and y is t squared. So this is really going to be this bit of the parabola over here, right? And let's integrate x, right? Why not? ds, and well, we just plug in the start plugging the thing, t. Well, there's nothing else. Now I need what's the speed. So first the velocity is 1 to t. So the speed is is square root 1 minus 1 plus squared plus 2t squared. So square root of 1 plus 4t, right? So square root of 1 plus 4t dt, right? Okay, and again, let me not worry about computing it, just for the purposes of time. Bore you with calculus 1, right? Those are just calculus 1 skills over here. So that's all it is, right? We write down what this integral is as a calculus 1 integral, and you can see that the reason why I'm well, maybe over here I could have maybe just so that I do integrate something today. Maybe let me come back to this this example over here, and let's do over this spiral. Let's do something that I won't be too lazy to integrate. Let's do z squared ds, because we've seen how this goes, and so 2 pi and z squared, z was t, so this is t squared times square root of 2 dt, and I can do this in my head, so I don't have to worry about doing some sort of a integration by parts. And so this is I'm going to have the square root of 2. There's going to be d cubed over 3 is the antiderivative, right? So this is over 3, and so there's 2 pi cubed, right? Okay, so just so that we can actually, we have actually done something. If on the exam or on a quiz or something, it'll be sort of simpler ones that or maybe I'll just ask you to write what it is if it's complicated, or if it's if I ask you to compute it, it's probably going to be a fairly simple one. Maybe one where you can easily do it without some integration by parts or something. Okay. Not that you shouldn't know integration by parts, but it's not a that's not the point of this class. That's you should have already known that. Now, this let's look at some application. Really, what it is. Well, it's giving us if we have a curve c, the integral of just integral of 1. Well, that should be in the units of right. It's if I think of 1 as a unitless quantity, then this should be in the units of just length, and so this is length of C. It's the length of a curve. How do we figure out the length of a curve? Well, it's this integral over here. So how do we actually compute it? Well, we compute it. We have to somehow parameterize, right? So we have this vector valued function which parameterizes C. So then the length of the curve just becomes speed dt, right? So in terms of x, y, and z, right, is square root of x prime squared plus y prime squared plus z prime squared square root dt. It is annoying. I mean, those square roots do become annoying. Now, I claim that you have actually seen this, right? You have seen this before. You have seen this formula in somewhere in Calc 1 or 2. I can't remember exactly where it is given, but basically the place that you've seen it is when it was the length of a graph, right? If you had a length of a graph of, let's say, g of x, right, from x was between a and b, right? So as a b, the x-axis is the y-axis, so this is y equals g of x. Then the length of this was given in Calc 1 or Calc 2, wherever it is done, is this 1 plus g prime of x squared dx. Now, I claim that this is precisely what we're doing here. Now, why is that it? Well, the graph, I can parameterize it by setting x equal to t and y equal to g of t, because that's precisely this graph, right? I'm just parameterizing by x, really, right? I could have made this x, right? This would have been x was x and y was g of x, right? Just naming it t, right? And in this case, c prime is well, it's 1 and g prime of t, right? So what's the speed? So the speed is the square root of 1 squared, right? 1 g prime of t squared. Well, that's precisely what's out here, right? Except there's a t here and there's an x here. But otherwise, I mean, that's going to be the same number, right? It's a different dummy variable. And actually, coming back to the previous page, over here, this was really the graph. This is where y is x squared, right? That was the thing was really the parameterization of the graph. All right, so that's what one application. So another application is if we have some sort of a wire or some or some something along a curve. Maybe it's the we have a river and it has a different density of some toxic substance or something. We might want to figure out, well, the total mass of the wire, or the total the total amount of the toxic substance. And so this is, this is again, we integrate the density. So you've seen something like this before. So if delta x, y, z is the density of a wire at x, y, z, right? So the wire could have different densities at different points. Maybe it's out of different materials. It's maybe different thickness, right? Then total mass is just the integral over of the density ds, right? The density is in the units, let's say mass per unit length. ds is in the units of length, so this is now in the units of mass, right? So that's how we know it is it is mass, right? I mean, so it's the same thing as before. You integrate the density to get total mass. So it's used in a bunch of other ways. For example, we can get and we'll actually see that later on when we if we integrate charge density, we get the potential, and we'll actually see the integral coming up with when trying to figure out the potential of a conservative vector field. And so this is, if we, the integral is can be thought of as sort of the net change, right, of a quantity if we're given if we're basically given the derivative. So the line integral, this path integral, can be used to compute these net changes. So, for example, potentials. So we'll talk more about line integrals next time, because this is one type of line integral. But next we're gonna use this to do another type of line integrals, which is an integral over vector field, and it's maybe a little bit slightly more complicated in what it is, but it will turn out it's less complicated to compute, right? Because over here the problem was the s, and it turns out that integrals of vector fields, strange, even though they're actually more useful in some sense, they're actually also easier to compute because they don't have that ugly square root in them, right? That's really what made all these examples that I was too lazy to do the Calc 1 stuff on, right? It was that square root. Well, maybe over here I just picked up a bad function, but over here it was like square root. I mean, unless over here the velocity was constant. Oh, right. Sorry, the speed was constant. The velocity was not constant. So if the speed is constant, then it's not too bad. But it's a little hard to actually always make sure that you parameterize a curve with constant speed. Sometimes it's just much more convenient to parameterize with non-constant speed. For example, over here, a graph, it's much easier to parameterize it as a graph. But then you get this square root. Parameterizing it not as a, basically you're not going to make anything simpler. If you're going to try to find a parameterization of this with constant speed, you're going to be computing this sort of integral anyway. So it's not like you would make things easier, really, unless you can sort of guess a nice nice parameterization. All right, so next time we'll do the line integrals of vector fields.